Hi there everyone, today we are going to look at probability trees. Okay, so there's quite a little bit kind of going on with this lesson and different kind of variations in terms of how you do it, and obviously a lot of it is dependent on the question that you are posed with. So let's kind of dig straight into it and see how we kind of get on. Alright, so the probability trees are used to calculate the probability of successive events. So that means one event and then something else happening, or two events happening. Okay, so for example, the probability Tim wins a game of tennis is 3 out of 10. So you'd argue that probably he wins 2 matches and draw probability to show this. All right, so it doesn't say that one impacts the other. It doesn't say that if he loses this one, this happens. It just says that probably wins a game of tennis is 3 out of 10. So we have to assume that it doesn't matter the fact he's playing 2 in a row, that will change that probability. All right, so drawing a probability tree, we put the branches on in terms of winning and losing, winning and losing. All right, so the first match and the second match, because they're the 2 games, and of course your win-loss, win-loss and win-loss. All right, so here we go. All right, hopefully you can see that. So you've got first match, second match, wins, he loses, and second match, wins, he loses, wins, he loses. And obviously dependent on if he loses the first match, then he might win the second match or lose the second match if he wins the first match and wins, lose. So that's kind of combination. So you win 2, win, lose, win, or lose, lose. So those 4 on the right side are the different possibilities of the outcomes of him playing 2 matches. Okay, so normally we'd put the probabilities aside them. So if you've got a 7 out of 10 that he loses, you've got a 3 out of 10 that he wins, which we're given, and that's consistent because it doesn't say anywhere else that he's impacted by playing the second game. It just literally says the chance of winning are 3 out of 10 regardless. So they're going to go exactly the same over there. All right, so that is a probability tree draw. Okay, we haven't asked to do anything just yet. Literally just kind of draw them. Okay, so to calculate probabilities of successive events, you multiply along the branches. So what we're saying here, this is the idea of independent events. All right, so one doesn't impact the other at all. And so what we're going to do is, if I want that one and that one, then I'm going to times the 2 together. All right, so if I multiply along the branch to find what the chances of him winning 2 games in a row, it's 3/10 times by 3/10. All right, so probability of win-win is 3/10 times 3/10, which is 9/100ths. All right, so that is the chance of winning both games. Not particularly good. All right, and then if I do win and a loss, then it is again 3/10 times by 7/10. All right, which is going to be 21 out of 100. The next one is a loss and then a win, so that's 7/10 times 3/10, which again is 21 out of 100. And then the probability of him losing both is going to be 7/10 times 7/10, which is 49 over 100. And what you should notice is when I add these here, these 4 fractions at the end, because these are all the possibilities when he plays 2 games, then these fractions in the end would add up to 1. All right, and you can check that if you wish, but I'll show you that this lot will add up to 1 as you go. All right, so you can check your answers by adding up the probabilities to get a whole. All right. Okay, so independent events. So the outcome of events show no effect on each other. All right, is the terminology. So the probability Sue catches the bus each day is 2/5. All right, I mentioned it in the previous one. So calculate the probability she catches the bus on Monday and Tuesday, and calculate the probability she catches the bus on at least one of those days. So we're not told to draw a tree for this one, but it's the same kind of concept as you've literally just done. The probability she catches the bus is 2/5, and she's going to do it twice. All right, so as before, so we're going to label it as bus, not bus, bus, not bus, bus, not bus. All right, and the probability she catches the bus is 2/5, so it's going to be 2/5 and then 3/5, because that's not, and then you add up to 1, and that's going to be the same for Tuesday as well. All right, so it's very much similar to the one we had before, in that one does not impact on the other. All right, so in terms of A, calculate the probability she catches the bus on Monday and Tuesday. Well, that's the bus on Monday, that's the bus on Tuesday, so it'll be that times that, which would be 2/5 times 2/5, which would be 4/25. Okay, times 2 fractions. Calculate the probability she catches the bus on at least one of these days. All right, so that means she's going to catch the bus either on both days or on one day. All right, so there's 2 ways you can do this, and I'm going to show you both. So it could be bus and bus, which is that one. I could do bus and no bus, which would be that times that. Or it could be not a bus and bus for that one, and that'll give me that. And it's going to be those 3 added together. All right. So that would be a way of doing it, is you work out all the probability of where she can catch at least one bus. So it's either 2 buses or 1 bus, and then add the lot together. Alternatively, and this is probably the one that sort of is the smart one, some of you will get, is that if I want to calculate who catches the bus on at least one of these days, well, if I work the probability of him not getting a bus at any stage, then if I take it away from 1, so if I work out this one at the bottom here, and take it away from 1, I'll end up with these 3. And it's an awful lot quicker, isn't it? An awful lot quicker. All right, so let's see what they do on here. So you can see they've gone for this one, they've gone for this one, and then they've gone for this one. So they've filled in the boxes, and the probably catches the bus on both days is this one, we've already kind of mentioned. And the probability that she catches the bus on at least one day is those 3, which I mentioned, which is that lot, which gives me 16 out of 25th. But what I suggested, and I don't know if you're paying attention, if I do 1 take away this, what do I get? I get this. I get this. I get this. All right, so there is a bit of a cheeky way of trying to find it a little bit quicker rather than thinking I need to add these 3. All right, so read the question carefully and see if there's a quicker way of trying to achieve it. All right, but nothing wrong with this. Nothing wrong with this at all. This is actually perfect right. All right, okay, let's move on to one where dependent events. So we looked at independent events where the probability does not change, but of course, chances are that if something happens in one circumstances, then it will probably have an impact on the following circumstance. All right, so let's have a look at it in terms of what that actually means in context. So, for example, Dan's got 4 pairs of pink socks and 6 pairs of blue socks. All right, that's what he's got. Calculator probably picks a pink socks 2 days in a row. Now we're assuming, I guess, at this particular point, that once he's picked a pair of socks, he's not going to put them back in his drawer. You would hope, but I hope they go in a wash basket to be washed. But of course, this is a bit of an assumption, but it says calculator probably picks pink socks 2 days in a row. All right, but I would say that this is one's going to impact the other. All right, certainly at the beginning of the week, something was going to impact the other. So we're going to draw a probability tree and see what that looks like. So we've got first day and second day. So we've got pink socks and blue socks, pink socks and blue socks, and pink socks and blue socks. Okay, so the probability of getting a pair of pink socks to start with is 4 out of 10, isn't it? It's 4 out of 10 total. There's 4 pairs of pink and 6 pairs of blue, so it's 4 out of 10 for this top one. All right, that means there are obviously 6 out of 10 for the bottom one. However, if he's picked a pair of pink socks from the first day and they've gone in the wash, he no longer has 10 pairs of socks to kind of deal with, and he's already got rid of 1 pair of pink socks. So this probability has changed, hasn't it? It's now 3 pairs of pink socks, and there are only 9 left in the drawer. It's changed, okay? And this probability has also changed a little bit because there's still 6 pairs of blue socks, but out of 9, isn't it? All right, so these 2 need to add up to 1. Hopefully you can see that. There's 3 out of 9 of the pinks, and there's 6 out of 9 blue. All right. Down here, slightly different scenario. If he takes a blue pair, all right, so if he takes a blue pair, there are still 4 pink pairs left. So this one over here is going to be 4 out of 9. And then here, because he's got rid of a blue pair, he's going to have 5 left out of 9 down here. So you can see these 4 probabilities have all changed because they are dependent on what's happened before them. All right. And again, you'll notice your denominators has changed also because something's been taken out and it's impacted there. All right. So now that we've got these all kind of written in, so that's our tree, we should be able to answer the questions now that we need to. So calculate the probability he picks pink socks 2 days in a row. So it's going to be 4/10 times 3/9. So here we go, which is going to be 12/90. So 4 times 3 is 12. 9 times 10 is 90. And it does simplify, but because it's probability, I think we're going to leave it. And then underneath, we're going to do the next one and the next one. I think we're just putting them all in. Yeah, we are just going to put them all in. So answering the first question is this one, so it's 12/90. All right, so let's have a look at the next one. So the probability picks one of each colour. All right, so one of each colour, it has to be these 2, doesn't it? All right, these are the only options you've currently got, is that one or that one. And again, think about what I'm saying, is that one or that one. So if I'm doing that or that, then I add the 2 fractions together. So it's going to be 24 over 90 plus 24, right? It's going to be 48 over 90. All right. I mentioned simplifying. Now, it doesn't matter with probability, all right? It really doesn't matter. No one expects you to simplify a probability. It's a probability as opposed to just a generic fraction. So there's little expectation for you to actually simplify it. If you did, it'd be absolutely fine. But just be careful that you don't make a mistake on simplifying. Okay. All right. Well, that's probability trees. If you need the practice, and I'm sure you'll benefit from doing so, please visit maths-school.co.uk. The website link is at the bottom of the page. And of course, you're more than welcome to obviously revisit this video at any point. All right. Well, thanks for listening.